Now, in this lecture, we will discuss the thermodynamics of blast furnace iron making. It is little elaborate compared to what I did the basic thermodynamics during the iron making, steel making in the first lecture. Okay. So, the concept covered here, it will be the oxygen potential of iron oxide and the blast furnace gases and their correlation, and then iron oxide phase stability diagram, direct indirect reduction, CO utilization and carbon efficiency. Now, this is the Ellingham diagram. This diagram I also projected earlier also. So, Ellingham diagram you are very well known, most of you know about this diagram. It is basically gives the relative stability of various oxides and mainly the pure oxide. It is the pure metal pure oxide system. And is y axis, that is this gives basically the oxygen potential, what is called the oxygen potential. Now, this oxygen potential, there is the y axis is basically the standard free energy change. Standard free energy change is basically the delta G naught is equal to RT ln of partial pressure of oxygen. Okay. So, that is the y axis, that is basically the oxygen potential of oxide, various oxide, and it is varying with the temperature. So, for example, this line gives you for the Fe2O3, that is Fe2O3. So, for Fe2O3, oxygen potential of Fe2O3 with temperature varies like this. This is the way it varies. And for Fe3O4, this is the oxygen potential of Fe3O4 and how it is varies with temperature, and this is for the FeO. So, for 3 oxides you can find how the oxygen potential varying with temperature, and it is very evident that partial pressure, that is the oxygen potential of Fe2O3 is much greater compared to that of Fe3O4, and Fe3O4 oxygen potential is greater than FeO. Higher oxygen potential means if you just keep this oxide in a reducing atmosphere, Fe2O3 will reduce fast because it has very high oxygen potential. So, and then Fe3O4 will be reduced and then Fe will be reduced. So, basically Fe2O3 to Fe reduction is not direct. First Fe2O3 will convert to Fe3O4, then Fe3O4 to FeO and then FeO to Fe, right. So, this is the relative stability of different oxides. So, that is the thing we can say, that is the relative, from this Ellingham diagram we can find that relative stability, FeO is the most stable and then Fe3O4 and Fe2O3 is the least stable oxide. Okay. So, among these 3 oxide, this is the least stable, and as we will see in the blast furnace, as the blast furnace gas has the higher reduction potential at the bottom of the furnace where the CO forms, and as the gas moves up, as we will see later on, that is this reduction potential basically decreases. At the upper part, reduction potential become very less because the CO concentration slowly goes on decreasing as you move very up in the furnace. But in that case, the reduction potential is less, but Fe2O3 with the reduction potential you can easily reduce that Fe2O3 to Fe3O4, even Fe3O4 can be reduced to FeO, but only FeO is quite stable, it requires little higher reduction potential. So, it will be reduced in the lower part in the middle of the furnace. Okay. So, that we have seen, that is the reactions, that is in the top part it is the Fe2O3 get reduced to Fe3O4 and then Fe3O4 reduced to FeO, and then little lower FeO get reduced to Fe. Okay. So, this is, now let us see how the oxygen potential of the gas changes as it moves up into the blast furnace. This is very interesting to see because how the oxygen potential is changes, because then also we can understand that thing. Just now we said that is it is the reduction potential of the gas which is just inversely proportional to the oxidation potential of the gas. So, how the gas potential changes, that is moves from the bottom to the top, that we have to understand. And you can see the oxygen potential just here at this point A, when the gas enters, right, gas entered at this point A basically gas enters around 1000 degrees centigrade, and its oxidation potential is around 0.4 kilocalorie per mole. Why it is so? Because you know the partial pressure of oxygen in air is around 1.21 atmosphere, So, if you make it RTLN of PO2, it will be 4 kilocalorie per mole roughly. So, here, so the inlet gas at 1000 degree centigrade has a oxygen potential of around minus 4 kilocalorie per mole. Okay, there is the blast furnace gas. There is the I can say it is the basically the air blast, oxygen potential of the preheated air blast just at the tuer level. And now, when it enters the tuer and comes in contact with the carbon, it reacts with the carbon forming the CO gas, right. So, is oxidation, is reduction, there is the oxidation potential will suddenly very much, that is the oxidation potential you can find, it will come here, here, here and at this point. It will just reduce to this point. Oxidation potential will suddenly reduce in presence of the carbon, because it will react with the carbon forming the CO gas. Suddenly its reduction potential will increase and the oxidation potential will decrease, and what will be the oxidation potential? It will almost follow the basically C plus O2 forming the twice CO line. So, you can find this value is coming around 150 minus 150 kilocalorie per mole, and that we can get from the Ellingham diagram. From this diagram we can know that this value will be around minus 150 kilocalorie per mole. Now, what happens as the gas moves up, okay, in the blast furnace, if you see the blast furnace is like this, and you have, this is the layers, alternate layers of ore and coke like this. So, this is say ore and this is say coke, this is ore, this is coke, this is ore, this is coke, ore, coke like this. And you have the gas, that is the raceway, and the CO gas is moving up like this, right. CO forms and it moves up. So, when the C, that is the here, when it come in contact with the carbon, its oxidation potential is there, and as it moves to the ore layer, here ore, basically Fu is there at this location. When it is, if in the lower part of the furnace, it is only the Fu will be iron ore if it is there. So, when it interact with the ore, then its oxygen potential will increase suddenly. Why it is increased? Because the oxygen from the oxide, that is the oxygen, because it will reduce the oxide FeO to Fe, and that oxygen will enter into the gas. So, when the gas will enter, there is oxygen will enter into the gas, its oxidation potential increases. So, oxidation potential will increase as the gas encounters the ore layer, and then subsequently when again it encounters the carbon coke layer, again the CO will form and its reduction potential will increase or oxidation potential will decrease. So, this is the way the potential again will come down, and when again it will encounter the ore layer, it will increase, right. It will increase and then decrease, increase, decrease like this. So, as the gas moves up, as we can find, there is a reduction potential, there is the oxidation potential, as I said, it is very low here, that is your oxidation potential here suppose, and then as the gas moves up, right, from here as the gas moves up, it moves like this, and then finally it will go like this. So, this is the way your oxidation potential will go, right. Initially it is low and then it will increase, it will fluctuate to some distance, and beyond that is oxidation potential will increase only, there is no fluctuation. Why? And this actually, this is the temperature, this is below less than 900 degrees centigrade. So, in the upper part, when the temperature is less than 900 degrees centigrade, then its oxidation potential only increase, because only the CO will reduce the iron oxide, iron ore. So, it will take the oxygen from the ore, so oxidation potential will increase, and reduction potential similarly decrease. So, it is the here basically its oxidation potential is here low, right, oxidation potential is low, and then it will fluctuate and then oxidation potential increases. As the gas moves up, its oxidation potential increases or reduction potential decreases. So, that is why you have found that here where the oxidation potential is very low, basically Fe2O3 will convert to Fe3O4, and then your Fe3O4 will convert to FeO, right. And in the lower position, your all the other reaction take place, FeO to Fe, FeO to Fe, will take place here, right. So, and so that is why this is the thing, and so here you can find as the gas ascends, its oxygen potential is increased in presence of Fu and decreased like this. So, gas gets charged and discharged, okay, up to 900, and beyond 900 this oxidation potential increases, as I said. Okay. So, no charging of blast furnace gas below 900 degrees centigrade. Charging means its reduction potential never further increase, because below 900 degrees centigrade there is no in situ CO generation. So, as I said, that is below 900 you have no in situ CO generation, and then only whatever the CO has been generated in the lower part of the furnace, that will only act as an reducing agent in the upper part of the furnace, right, like for reduction of Fe2O3 to Fe3O4 and all these things, Fe3O4 to FeO. So, that is why that is called the indirect reduction to some extent. And so, I will come to that direct reduction, indirect reduction, but you can understand now why it is happening, that why the sequence of reduction take place in different part. Now, we come to the FeCO phase stability diagram. This is a very important diagram in because I was discussing the process in terms of oxidation potential. I think it is better to describe the process in terms of the volume percent of CO into the blast furnace gas, because initially at the 12 level everything is CO. As the gas moves up, it take up the ore oxygen and forming some amount of the CO2. CO get converted to CO2, CO get oxidized to CO2, and iron ore get reduced to the iron, right. So, as a result, basically as the gas moves up, it is basically a mixture of CO and CO2, and composition of the CO and CO2 in the gas changes, and that shows basically the what is the potential of the gas, reduction potential of the gas, you can understand from there. Now, you can find this is basically the equilibrium line. This is the equilibrium gas composition in the blast furnace, and this is dictated by the reaction that is called the Boudouard reaction, that is called the Boudouard, Boudouard, Boudouard reaction. Boudouard reaction is basically your CO2 plus C forming twice CO. So, this reaction is also called the Boudouard reaction, very important reaction, and that this reaction only gives what is the equilibrium composition of blast furnace gas at any temperature. Okay. So, that gives you, this line gives you the equilibrium composition of the blast furnace gas, and these are the lines, these lines show you the equilibrium line between FeO-Fe equilibrium line. So, if the gas composition is here somewhere, so you can expect that iron will be stable here, okay. And in this region, because this region is below it, so FeO will be stable, and this line basically Fe3O4 to Fe equilibrium, Fe3O4 plus CO forming FeO plus CO2. So, in this you can understand this is the equilibrium line for Fe3O4 and FeO. So, below this any gas composition above it will give you the FeO, and below it is Fe3O4. That is why Fe3O4 is stable in this region. In this region, it is the FeO that is stable, and above this here it is the Fe, iron, that is stable. And Fe2O3 is stable at a very low percentage, volume percentage of CO. You can find Fe2O3 get converted to Fe3O4. So, we do not find any Fe2O3 phase in this diagram, because it is almost, it get reduced instantaneously at a very lower volume fraction of CO. So, you cannot find it, maybe below this line some amount of Fe2O3 is there, but most of the cases here it is Fe3O4, FeO, Fe, and also at lower temperature here also you can get some direct reduction of Fe, you can get Fe here also. So, what you get, that is the thing, this is basically gives you, basically here this FeCO phase diagram is nothing but volume percent of CO is plotted against temperature, and different stable phases are shown in this diagram, right. And now, let us see that equilibrium percentage CO required to reduce Fe2O3 and Fe3O4, Fe2O3 to Fe3O4 almost 0, as I said, but at 900 degrees centigrade Fe3O4 to FeO reduction, Fe3O4 to FeO reduction, if I say at 900 degrees centigrade Fe3O4 to FeO reduction, how much? It takes around 20% of, you can find this is the 20%. This is the 20%. So, 20% volume percent of CO is required if you want to reduce, at least it will be in equilibrium, that is Fe3O4 FeO. In this equilibrium, 20 volume percent of CO will be in equilibrium. What does it mean? And for FeO to Fe equilibrium, around 70% CO will be in equilibrium with the FeO-Fe system. What does it mean? It means that if you want to convert FeO to Fe, then you have to have volume percent of CO in the CO-CO2 mixture. Basically, when I say volume percent of CO, it is basically in the CO-CO2 mixture, without considering the nitrogen and all this. So, if in the CO-CO2 mixture, volume percent of CO is 70%, okay, then you won't be able to read that, then FeO and Fe will be in equilibrium. If you exceed that volume percent of CO beyond 70%, then only you can reduce FeO to Fe. So, it means you can utilize only 30% of the CO for reducing the iron oxide, FeO to Fe. Similarly, for Fe3O4 to FeO, Fe3O4 to FeO, you can utilize here 80%, 20% will be in equilibrium. So, you can utilize 80% of the CO. But in case of FeO to Fe, 70% will be in equilibrium and you can utilize only 30% of the CO. So, percentage utilization of CO is 30% for FeO-Fe conversion and 80% for Fe3O-Fe conversion. And as a result, you can write, this is the equilibrium equation you can write. For FeO-FeO conversion, this is the equilibrium reaction that you can write. FeO plus 3.3 CO. How the 3.3 factor comes? 3.3 factor comes because you require 100 by 30, because 30% only you can utilize 100%. So, this gives you 3.3. This is the factor is coming from here. So, FeO plus 3.3 CO, it will form Fe plus 2.3 CO will be in equilibrium with the CO2, 1 mole of CO2. So, this is the equilibrium reaction. Similarly, for Fe3O4 to FeO, your equilibrium reaction will be like this, because here it comes from 80% utilization you have, 20% in equilibrium, 80% utilization. So, 1.25 mole of CO will be required to reduce 1 mole of Fe3O4, and 0.25 mole of CO will be in equilibrium with 1 mole of CO2. So, these are the equilibrium reactions. So, actually this is the reaction that you take place, this much of CO is required, it is not the 1 mole of CO will convert the FeO to Fe. Okay. So, at 900 degree centigrade, Fe requirement is quite high. And another thing you can find, that is this is the actual blast furnace gas and this is the equilibrium blast furnace gas. So, always you can find that the blast furnace gas remain too much unutilized because of kinetic limitation. It is not that the blast furnace will be in equilibrium. So, equilibrium gas composition you may not expect into the blast furnace, although this line shows to be very non-efficient, not much efficient blast furnace. In a very good blast furnace, this line may come here also. Okay. Thank you.